So even though the entire last section was basically an example to illustrate PageRank, let's take a look at another similar case just to illustrate the main ideas again and hopefully crystallize some of the math behind it. So in this example, we again show 4 nodes here. We have nodes A, B, C, and D, and we can denote their importance scores by lowercase a, b, c, and d. And the first thing we have to check for is 2 things. First, whether or not we have any dangling nodes, and the answer to that is no, because each node points to at least one other node. And the second thing is whether there are any unconnected components of the graph, and again that answer is no, because we have connectivity between each of the nodes. So it's possible to get from any node to any other node, even if you have to go indirectly through a number of nodes. And so we don't have to make any modifications here, and we can just do the PageRank in the typical sense without adding any of the randomization in. And so we can go ahead by start to write these equations out. The first one for node A is we note that D has an out degree of 3. So we say that A is equal to D over 3, because D is A's only incoming neighbor. We say that B is equal to D over 3, because it has an incoming link from D, plus A over 2, because A splits 2 ways. And we say that C, since C has 3 incoming links, C is A over 2, plus B over 2, plus C over 3. And finally, D has 2 incoming links. It's B over 2, plus C. And we can also write these on the graph if we want. We can write A over 2 on this link, A over 2 on this link, which helps us come up with these equations in the first place. This is B over 2, since B is an out degree of 2. This is also B over 2. This is D over 3, D over 3, D over 3. And this is just C, because C only has one outgoing neighbor. So now we can start to run through the calculations for PageRank. And in order to do that, first thing we have to do is choose which one we want to get everything else in terms of, and to plug into the normalization equation that A plus B plus C plus D is going to be equal to 1. So if we go back to check out our equations from the previous page, we see that we already have a simple relationship between A and D, just that A is equal to D over 3. So it looks like it would be very convenient if we got everything in terms of D, because we already have A. That's already done. So we already have now that A is equal to D over 3. And then we can similarly say that B is equal to A over 2 plus D over 3, which is D over 3 divided by 2, or D over 6, plus D over 3, which is equal to D over 2. And for C, we want to avoid C's equation of 3, and instead use the simpler equation that we have already, that D is equal to B over 2 plus C. And so that leads us to say that C is D minus B over 2, which is simply D minus D over 4, which is 3D over 4. So this example is similar to what we had before, except the graph is slightly different. And so now we can use that and plug into our normalization equation. A plus B plus C plus D has to be equal to 1. And using the relationships that we just got for each of the variables, we have that D over 3 plus D over 2 plus 3D over 4 plus D has to be equal to 1. So therefore, if we add all these fractions up, 1/3 plus 1/2 plus 3/4 plus 1 is equal to 31 over 12. So that tells us that D is 12 over 31. And similarly, we know that B is D over 2, which is 6 over 31. That C is equal to 3D over 4, which is 3 over 31. And that D, we already have D, 12 over 31. But finally that A is D over 3, which is just 4 over 31. So if we ranked these, we would have D being the most important, then B being the second most important, which would be followed by A, and followed by C, which would be the least important. So this is how Google would show on a search result page.